Greetings, humans. It's time to work on the brains portion of chapter 3. Good. So just sort of a systems perspective here. We can break down the nervous system like this. Part 1 is going to be the central nervous system, or CNS, and that's the brain and the spine. Okay. Neurons all through the brain and spine. They are connected to each other, they terminate in other neurons, they are interneurons, and that's really what makes them the central nervous system. Thought, cognition, what we classically think of that, all the action is in this part of the CNS. But your spine also does make some decisions, like pulling your hand away from something that's hot, okay? So reflex actions are in the spine. CNS. PNS, or peripheral nervous system, that's everything with nerves that isn't in the brain and the spine, right? So you know that you have motor neurons that terminate in the environment, in your fingers, in your hands, in your arms, in your right all through the body. You have nerves, and they connect to the intestines and the kidney and the liver, so the brain can tell the organs what to do and get information from the outside, right? So all that stuff is peripheral nervous system. And then we can break the PNS down into 2 parts as well. Okay, so the sympathetic nervous system, that's all the parts of the PNS that are responsible for making us agitated. There's a threat in the environment or a perceived threat in the environment, and this is the system that's dumping adrenaline and cortisol into your body and getting you all crunk so that you can take on whatever challenges. I apologize for the crunking. Whatever challenges are out there, right? So the fight and the flight you've heard of, the freeze, which is usually just a conflict between fight and flight. And there's no programmed resource, and we're all amped up, but nothing, no like response to the situation. You just like rabbit in the headlights. Deer, Americans would say deer in the headlights. Okay. And then the parasympathetic nervous system is really just the emptying out of the sympathetic nervous system, where you're dumping adrenaline and cortisol out of the system, right? Using it up, get rid of it, and returning just to normal operations where you can digest last night's tacos and think with your frontal lobe. Okay, mostly what this is good for is it's a good example of a hierarchical system, and that's going to be important for us when we get all the way to chapter 6 and talk about memory, organizing things into these sort of flow charts and hierarchies. Allows us to encode and retrieve a lot more information more efficiently. All right. So as we start talking about brains, to me, the most important question is, how do you know that, right? Where does that information come from? How do you know it's reliable? So that's the epistemology part of the problem. Epistemology, the study of knowledge, how do you know? Okay. So in the olden days, right, how we know is that people would hit their heads, and you'd see their behavior before they injured their brain, and after they injured their brain, you'd see damage, and you'd start to go, hey, wait a second, this change in behavior correlates with damage to that part of the brain. So like the famous example in every Psych 1 textbook is Phineas Gage. Gage is a railroad worker, late 1800s, and he's just a normal dude for a railroad worker, not exactly the highest status occupation in the United States, but he does his job. There are camp followers and co-workers and bosses, foremen. He gets along, he shows up to work when he's supposed to. He works hard all day. He goes back to camp when he's supposed to. He doesn't get into more fights than anybody else. Yeah. The ladies don't complain about him, But one day a charge goes off prematurely, right? They're using dynamite to blast the land level so that they can build railroad through it. And he's too close to a charge. And the charge picks up, the explosion picks up a railroad spike. Like when 9 Inch Nails is talking about 9 Inch Nails, those are really the nails that they're talking about in the name of the band. And which is really just one guy, which is weird. Anyway, the railroad spike is flung through the air and Gage is knocked down by the blast, and then the spike takes him up under the throat. It goes in the right side, and then miraculously it doesn't damage his trachea, and miraculously it doesn't puncture the artery that's on that side. I can't remember which, the carotid, and it goes up through his soft palate and through his left eye. It pops his left eye, and through the left prefrontal cortex, which I don't think is called that at the time, but still, that part of the brain popped. And a series of miracles ensue, right? It's miraculous. It's really low probability that you'd survive an injury of that nature, that it would just push the windpipe and the artery out of the way and not damage either one, because with the medical technology in that time and place, right, that would be just fatal. You're done. What else? He doesn't bleed out. That is such a low probability event. And he survives the extraction, right? There's a time when doctors aren't washing their hands when they do surgery. It's just a camp doctor, Amazing, absolutely amazing. And there aren't antibiotics. He doesn't die subsequently of infection. They don't have penicillin even. He makes a more or less full and complete recovery and returns eventually to work. But then we have this picture of Phineas Gage before and after this traumatic brain injury, right? And before, he's just a regular working guy. And a regular working guy would have problems. He wasn't a perfect person, But after, he doesn't show up on time. He shows up when he wants to. He's fractious. He gets in a lot of fights. He argues with the foreman. He's handsy with the ladies. The ladies now, the camp followers sort of set, are complaining about it. And so we start to learn from this event and events like it that the frontal lobe, that part of the left prefrontal cortex, is really responsible for inhibition, right? Deep down in your brain right now, you have all sorts of ideas about what you could be doing. Hurling profanity at the TV screen, running into the streets naked, hitting people, right? And your frontal lobe is there to say, no, don't do that, right? This is the appropriate behavior for the context, and we're going to limit all of the other behavior that the motor cortex and the limbic system want to kick up. We'll talk a little bit more about that later. How do we know? We know that first from studying people with TBIs. And then through a similar process, people who get sick, we would see their behavior change in their lifetime. We wouldn't necessarily have an explanation for that, but a post-mortem analysis. When someone dies and you can crack open their brain case and compare their deceased brain to other deceased brains from people who didn't have those problems, you can start to correlate damage, abscesses, cysts, lesions, tumors, with changes in behavior, and start to get that initial picture of this part of the brain does this function, okay? Surgery. So you're poking around in someone's brain because you need to do surgery. And as long as you're in there, in the past, at least the 90s and 2000s, now not so much, you'd have to be awake for a brain surgery. We need to monitor your level of consciousness so we know that, because your brain is your consciousness, so we know, like I was there, that we're not causing any collateral damage. So as long as you're in there, you can use electrodes to stimulate different parts of people's brains and then see how that affects their mental process, right? So let's have you do math problems while I'm putting electrical current and disrupting your parietal lobe. And then I see, I can demonstrate that the parietal lobe has at least something to do with your math ability and your arithmetic ability, stuff like that. So that's another way. And then if you're doing psychosurgery, and excising parts of the brain, and you could compare before and after observable behavior. All that stuff's intrusive, and you don't want to sit around and rely on people getting brain injuries. And of course, it would be immoral and unethical to lesion people's brains and do it on purpose, but certainly in America, we do it to animals. And certainly in other countries, it's done to humans for purely experimental reasons. And we're not happy about those sources of information, but we have them. Okay. But they're unobtrusive, unintrusive ways to get information about brain behavior correlates. And one of those is the electroencephalogram, or EEG. Now, if you get the chance to say electroencephalogram, you should say it because it makes you look really smart if you could just toss it off smoothly. Even better is if you can say electroencephalographic analysis. People will be very impressed. But if you can't do that, EEG is fine. Everyone knows what you're talking about. So this is a series of electrical contacts that sit on your scalp. They attach with a little bit of adhesive, and this is really portable, actually. And then each of the contact points is usually going to have an electrical lead. Now you can gather all those together, and you can wear a hat over it and hide the cord down the back of your shirt, wear a pager. It's pretty primitive. You're going to get that sort of, you've seen the paper readout with the pencils going up and down, and the little colored pens going up and down. You're going to get brain wave readings, right? And it takes a certain amount of interpretation to know what those brain waves mean. And you're going to get largely surface level data. We talked about neurons firing, right? And those neurons firing kick off electrical discharge, EMI discharge, that can be measured across space, especially if you're really close. You're going to get a surface level, what are the outer layers of the brain doing? The inner layers, that's going to be a little bit confounded by what the outer layers are doing. With time and training, you can get a pretty good picture of what parts of the brain are doing what at a given time. With all this other technology we're going to talk about, why is that useful? You can get much better information from other methods, but this method is so portable. You wear it on your head and it goes to a beeper, and it sends telemetry to the doctor's office every 15 minutes or hour or whatever they set it up to do. So let's say someone's having a seizure disorder. We can glue these contact points to their scalp, and we can send them home for 2 or 3 days or even a week or something. If you're having seizures, what am I going to do? Like, stuff you in the fMRI tube and lock your head in place and tell you to lay still for the week or a month or a year it takes you to have a second seizure or not? Right? It's ridiculous. It's expensive. It's impractical. This is so portable that even though it's not the best, clearest, most obvious data in the world, searchlight effect here, it is what you can get, and therefore very, very useful. So it's really why EEG is still around, is the portability of it. Computer-assisted tomography, or CAT scan, or sometimes CT scan. So this is the one where you're going to drink a radioactive solution first, usually barium, and wait a little while so that it can infiltrate into the bloodstream, into the fine parts of the bloodstream, the capillaries that run all the way through the brain. And so you can just see where blood is in the brain, and that'll give you at least that level of view of neuroanatomy. So gross deformity or abnormality can be detected, fine problems. With time and training and clarity and luck, sometimes really small deviations can be found. But this is really a big picture thing. CT or CAT, really a big picture thing. Positron emission tomography. This is Star Trek stuff right here. Because literally what we're doing is grabbing matter and antimatter and colliding them so that it produces positrons, and we're throwing positrons through the brain. Positrons interact with matter, and we're measuring how long it takes positrons to get to the other side. So the time difference between vacuum and matter is telling you how much matter and therefore how dense the matter is. And so a computer is going to put all that together and give you sort of a ghostly grayscale readout of what the positrons pass through. And if you do it at various angles, right, then you can get comparative density and get actually quite a nice picture. Again, largely of gross neuroanatomy. Fine neuroanatomy is harder to get, harder to get at a level that can be diagnosed. Okay, so if you're looking for tumors, this is a great one. The modern standard, the gold standard though, is fMRI. MRI is magnetic resonance imaging. Blood platelets contain iron. Everyone knows this, right? Blood platelets, iron, cool. Well, iron disrupts magnetic fields. So what we do is we put a magnetic field around your head and then measure the way that your blood flow disrupts that magnetic field. Get it? And then computers, being much smarter than we are, at least able to do loads of calculations per second, can extrapolate where blood must be in your brain to be causing the magnetic field disruptions that we observe. Okay? And the neat thing about this is you can start to do that in real time. So MRI initially is just a snapshot, and it takes a long time to actually turn that snapshot into a picture that you can look at and interpret and make meaning of. It's not simple. It's not right there in front of your face. But fMRI is doing that over time. So it's more like making a movie of the brain, and in particular, which parts of the brain are experiencing a rush of blood flow. So this is going to look like, eventually, with a ton of computer rendering and preparation, it's going to look like that picture you see of a brain with certain parts of the brain lit up because they're more active than other brains. Generally, that's about 10% of the brain at a time. This leads us to the modern myth that people only use 10% of their brains, and if they could use more than that, then they'd be geniuses, right? They'd be brilliant. And every few years, a movie comes out about it. What is it? Lucy with Scarlett Johansson. Before that, it was Phenomenon with John Travolta. And then, isn't there a movie about a bicycle courier who takes a drug that does it? Something like that. It's just total crap, right? And if you thought about this for 15 seconds, you see that it was total crap. Just because one part of the brain is lit up on an fMRI, it doesn't mean that other parts of the brain aren't doing anything. It means that we've detected that part of the brain has an uptick in blood flow. More blood flow is going to this part of the brain than other parts of the brain. It doesn't mean the rest of the brain is shut down. Okay? Think about it. Why is your heart beating right now? Exactly, because your brain is telling it to. Down in your brain stem, there's this like metronome signal going out. Beat, 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 and it's telling your heart to pump the blood. And if we stab you in your brain stem and that signal's not going out anymore, your heart stops, right? Okay, so if you're looking at the fMRI and we're telling the people now do some math and then measuring where blood flow changes, right? The parietal lobe lights up because they're doing math, and that's where math lives. If you can only activate 10% of your brain at a time, then when you did math, you would literally die. Isn't that the dumbest thing you ever heard? Right? The rest of the brain doesn't stop what it's doing. But it does concentrate effort and energy to accomplish specific tasks at specific times. Okay? So that's MRI, fMRI. And we can take all this much too seriously. There is really an aggressive program to convince people that you are your brain, you're nothing but your brain, and your brain predetermines everything about you. You lack choice, in other words. So watch these videos. This is, gosh, I've forgotten her name already. The title of the talk is called Neuro Nonsense. And this is just a person breaking down how popular titles, including men are from Mars, women are from Venus, and so forth, really make far too much of the findings of neuropsychology. In one case, the imaging study was done on like a dead fish, a trout or a salmon or something. They exposed a dead salmon to a stimulus, and then part of its brain lit up. And this got taken and extrapolated and used to say something about with high degrees of certainty. It just is totally, totally undue. This is a frontier. It's a new frontier. In as much as we've only been doing this stuff for 40 or 50 years. So, I mean, there's that. Oh, I meant to add another thing in here. Hemispheres, and then you're going to actually see me look for the video I want you to watch on this. Hemispheres. Okay, cool. I'll try to do that efficiently, no promises. Where are we? We did neuro nonsense. So here's the scary part, the neuroanatomy part of the lecture. And I have to be honest, I don't care about neuroanatomy any more than I care about neurotransmitters. Just like mark the pages in the book that have the dialogue on which part of the brain is doing which thing. I'm going to try and give you a generalized picture of the parts of brains that are going to keep coming up through the lecture because they have to do with what we're talking about. But look, I've been a psychologist for 10 years, and I've worked in psychology since 1998, however long ago that was, like 22 years at the time of this recording. And never once has it really been relevant what someone's brain was doing. The appropriate level of study for human beings is the human being in front of you. And the temptation to like break people into parts that you can understand is dehumanizing and usually not very helpful, right? Never in my history of work in psychology has someone come to me with a problem. Hey doc, I'm really depressed right now, or whatever it is, or I'm thinking inappropriate sexual thoughts about something or whatever. I've been like, hang on a second, I need to get my microscope and see. Never, it's never happened. Never has brain information been of use in my career in psychology. So, I mean, just read the book, mark the relevant pages, and it is part of the course. I'll try and give you this sort of general topography you're going to need so that we can understand what we need to, but not more than that. You know, read the book, take the test, forget about it. If you're really interested, like take a neuroanatomy course in university, you know what I mean? Like that. Okay, good. So we can talk about ages and location. This is topography. So the fore, mid, and hind brain roughly correlate to evolutionary stages of development. The hind brain, or the stuff, it's really the stuff at the bottom more than at the end, the brain stem and the limbic system. This stuff is the most ancient. So everything that's ever had a brain has had these brain regions, right? So you can make snap impulsive survival decisions based on input from outside. And then the midbrain comes along a little later, and this is largely about interpreting sensory stimuli, getting a bigger, grander picture of the universe, better senses. And then the forebrain comes along much later, in more than a trivial capacity. Only mammals even really have it, right? It develops from the olfactory bulb, interpreting scent, grows out from there and starts to do more and more complex reasoning and inhibitory functions, delaying gratification. Okay. So the frontal lobes, or the forebrain, What are they for? The front third of the brain, inordinately expensive to run and operate. What do they do? Abstract reasoning, largely. With the parietal lobes, which really live kind of there, that sort of zone, thinking about things in the abstract, time, things that aren't in the room with you, like close your eyes and think of Neptune spinning through the infinite dark cosmos. You know? Neptune's not here, but you can still think about it. Your frontal lobes are doing that. Okay. The future. What is life going to be like in fall semester? I don't know, but I can think about it and I can try to use reason to make some predictions and extrapolations. Okay. Not emotion necessarily, but making sense of emotion. Okay. Most of emotion originates in the low brain, and then we decide what it means in the high brain. We take it from a felt sense or a feeling state into a fully fledged, mature adult emotion up here, and then make decisions based on it. It's the inhibitory complex, it's the brakes. The body wants to do stuff. The body wants to eat and have sex and murder other people because they're threatening. And the frontal lobe is going, let's don't do that. Okay? Thank you for using your frontal lobes. The unified integrated experience. When we get into chapter 4 on consciousness, this is going to be pretty important, actually. Each part of your brain is off doing its own individual thing all the time, right? But then it's sending its computations forward to the frontal lobe, and the frontal lobe is grabbing each of those data streams and wrapping them up and experiencing reality like all at once, not in a fragmented fashion. You don't see on one stream and hear on another stream. You see and hear at the same time, right? And what you see depends on what you hear and vice versa. Okay? Sort of long-term strategic decision-making. Your values. What do you value? What is good and bad in your estimation? Well, it takes a lot of inhibition actually to enact what you think your values are. And most of the time you don't. Most of the time your limbic system is making snap decisions really fast. Again, we'll see this more in the consciousness chapter. And the frontal lobe then is deciding, what do these actions we've taken mean in light of our values? Very rarely do you actually feel any guilt or anxiety. Your brain defends you from this by changing your values to match what your limbic system did. Very dangerous. So that limbic system, kind of down next to the brain stem, it has much quicker access to the motor cortex and sometimes to the spinal cord and the glandular system. So the old brain, the lizard brain, really is in charge most of the time. It takes effort to stop, relax, wait, think it through, and then decide to override. Okay? So what lives in here? The hippocampus lives in here. The memory cortex. The hippocampus is not the file cabinet, but it is the file clerk. It knows where all the bodies are buried. It knows where in the brain the memories are stored, and it can point at them and access them when you need them. Damage to the hippocampus is bad. You can't make new memories or access the old ones. amygdala, or the amygdala. This is the sort of the 90s girlfriend all the comedians were complaining about. She is always scared or angry. Okay? Amygdala feels fear and anger and really doesn't do much else. Decision making short term. Comparing incoming stimuli with stuff in the memory system that is threatening, right? Does it have claws? Is it coming at you fast? Is it fiery? Is it heights or clowns or big teeth or particular smells? Well, those things trigger the amygdala to trigger this glandular interface to start making self-defense sort of oriented decisions. Down in there somewhere, you're going to find the hypothalamus. And the hypothalamus has 4 jobs that all start with F. Fighting, feeding, freezing, and sex. Those are the 4 Fs of the hypothalamus. Really old neuroanatomy joke, sorry. Fighting, adrenalizing, and self-defending, right? Fight or flight, that's that thing. Feeling hunger, that's in the hypothalamus. Calories are dropping, blood sugar is dropping, produce hormones that stimulate your stomach to go after food. Temperature regulation and the need to reproduce. Okay, so very much of human activity really is about this tension between the long-term needs of the frontal lobe. These are my values. This is what I want from life. This is how I'm going to survive a year from now. And the short-term demands of the limbic system, right? This is what I hate. This is what I fear. This is what I'm hungry for. And Uncle Siggy, Freud, Johnny on the spot in the 1800s, early 1900s, going, we can map the mind, right? In the abstract, we can map the mind. Freud kind of detected this conflict, and without knowing any neuroanatomy really to speak of, came up with this idea of the id, the ego, and the superego. Okay, so the id would be that sort of libidinous urge self, the limbic system really saying, I'm hungry right now, you need to feed me, I'm sexually aroused right now, or I'm scared, or I hate somebody right now. And that, right, that level of impulsive action versus the needs of the frontal lobe to fit in with society, right? Your internalized standards. In America, we shake hands and make eye contact. And even though it's uncomfortable for people to do that, you push through it and you override the limbic system's urge to look away or dominance or whatever, and you enact the polite manners. And those things are in tension. They're in tension all the time. Was Freud right about this? I mean, a little bit, yes, a little bit. On the big picture, yes, in the specifics, not very much. And then, he'd say there's the ego, which is the mind making the decisions between the limbic system urges and the internalized standards of society. And those are rough analogs for the limbic system and the frontal lobes. There is no person scaled down sitting between those things. They just compete. Okay. And then we're going to have the perceptual systems. These are going to come up. So we're talking touch and hearing. The parts of the temporal lobe are doing those functions. When we're doing vision, that's the temporal lobe. It kind of sits just behind the frontal lobe. It's kind of here-ish, right, like that, kind of in the cone. There. And then the olfactory bulb, it's in the back right there. Oh, cerebellum, I didn't put on the list. She's going to come up a little bit. Cerebellum is kind of under the brain, and it's almost a separate brain with a different texture. And she coordinates complicated planful movements. All right. Occipital lobe right here, and that's doing vision. It's doing 4 parts of vision in parallel. So there's a part of the brain processing form, and a different part of the occipital lobe processing color, and a different part doing movement, and a different part doing form, color, distance, spatial awareness, right? So those 4 things happening in different parts, and then they're unified and coordinated into one picture, and then sent forward to the frontal lobe to be made conscious. The olfactory bulb, sort of there, yeah, deep, kind of a bit behind the nose. sort of behind the frontal lobes. And that's where you're doing odor detection. Don't ask me where to find taste. I just don't care enough to know. Speech systems, these are going to come up. So kind of like here-ish, each one maybe the size of a quarter. So Broca's area sort of right there, Wernicke's area kind of right here. And Broca's area is doing speech production, taking the complex abstract thoughts and making those into words, and then coordinating with the cerebellum to produce the complicated oral and chest, diaphragm movements and larynx movements necessary to produce the sounds that coordinate with those words. Or if you're doing sign in exactly the same way, coordinating the hand movements necessary to produce signs. Wernicke's is doing speech reception. So processing parts of incoming sound that are words. It has to detect which are words and which are not. That can lead to some confusion. But grabbing the words, either visual, reading, or spoken, or seen, sign language, whatever the language is, and rendering the words down into their abstract base components. Okay, and then hemispheres, and here's where I need to go to the YouTube and find you a video, which if I were a smart person, I would have done before. Much has been made of left and right hemispheres, and I'm just here to tell you that almost everything is bilateral, right? Whatever functions you have on the left, you really have on the right, and whatever functions you have on the right, you really have on the left. There's really not such a thing as hemispheric dominance. And if you've been on Google trying to find out about yourself, whatever, and taking those tests, they're just crap. There's not good empirical evidence to support those kinds of assertions. Here we go. I have about a 10-minute video for you. It's old and crusty, but very informative. And when we get to consciousness, again, this is going to be really, really important. There. So there it is in your screen. Okay. There are some functions that are lateralized. Almost everything, though, is bilateral and unified. So the corpus callosum sits kind of under and between the hemispheres, and it's this like cone-like structure, and it is really grabbing right hemisphere stuff and sending it left, and left hemisphere stuff and sending it right, and then all that gets coordinated and sent to the frontal lobes to be made sense of, like all together in one unified experience. The idea that right brain people are more artistic and left people are more logical and all that stuff is really absolutely nothing to it. When it comes to control of the body, what you need to know is control is contralateral, meaning that the right brain controls the left side of the body and the left brain controls the right side of the body, right? And input, the same. So right eye goes to left occipital lobe, left eye goes to right occipital lobe, like that. So contralateral control. And just a couple of little functions are lateralized. So I pointed to my left lobes to call Wernicke's and Broca's area, right? But you also have a right side Wernicke's and Broca's area. Okay, Broca's, Wernicke's. It's just that for almost everybody, for at least 95% of people, the syntactic part is happening over here. That is, what do the words we're saying actually mean? That's happening on this side. And then for 5% of people, that's happening on this side, maybe as much as 5%. Nobody knows why. Nothing to do with being left or right-handed. Forget it. No correlation. It's just a weird thing. But on this side, what's happening is like the emotional qualities of speech. What we call the prosody or the musical intonations, the ups and the downs in volume and pitch, right? Pause and cadence, speed, and all that emotional import, which is often most of speech, right? It's only kind of, we call it locus valley lockjaw. This is a real thing, actually, where higher class white people tend to speak without any emotional content. That they mean only the content of their speech, only what the words mean is what they mean. And other people, people of color and lower class whites, middle and lower class white people, tend to mean more the emotional content of their speech. To talk with your hands and your bodies and your faces, and not just like Stephen Mnuchin giving a briefing from the White House. Seems like such a cold fish, right? The Secretary of Treasury, everyone hates him because he talks with locus valley lockjaw, and he just seems so arrogant and out of touch. It's just the he only means the things that he's saying, and right, nothing else. So these are real things, and you can weigh and measure and study those. So what does that mean? It means if someone were to damage your right side Wernicke's area, then everyone you were listening to would sound like Stephen Mnuchin, right? Everyone you were listening to would be reduced to only the content of their words. You would hear none of the intonation or prosody, right? Yeah. There would be no emphasis on the right syllable for you to understand. On the other hand, if we were to damage your left side Wernicke's area, then all you would hear would be the sounds of the language with no meaning, but you'd get all of the emotional import, right? It'd be like living in Charlie Brown world where adults all go, wah, 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 wah. Okay? You can get by on that, actually, because most of what most people mean is emotional anyway. Okay, what else is lateralized? Have a look at this video. I want you to see it. It'll blow your mind. Yeah, watch it. Have a good time. If we were meeting in class, I would show you this video in class. I would like if you could take the time to do that. Okay. And then kind of the last thing, this will be more towards the end when we're talking stress and stuff, but you need to know about the HPA axis. We refer to the brain often as the fast system and the glandular system as the slow system, even though parts of it aren't all that slow, okay? So the HPA axis is the hypothalamic pituitary adrenal axis. Okay, so some hormones can be quite fast. Your brain detects a threat, and the hypothalamus hits the pituitary, which hits the adrenal glands on top of the kidneys or wherever they are, and they start pumping out adrenaline and cortisol. Even before you're aware you've detected a threat in the environment, because your frontal lobe is behind your limbic system, right? You're already getting juiced up and ready to go. That can be pretty quick. But the pituitary mostly is doing slow stuff, like lifetime stuff. The right genes activate at the right times, and it tells it itself produces growth hormone, right? So that babies grow up to be cowboys or whatever babies grow up to be in America. Right, you get bigger at the right times. You're programmed to convert nutrition into bone growth and muscle growth at particular times of life. And that happens over the course of your lifespan. That growth hormone production slows and eases, and it comes back a little bit now and then, but it eases and eases, leads to like the easing of that leads to bone density and muscle mass loss as you age, because you don't need it and shouldn't be consuming resources, all that stuff, evolutionarily speaking. And so that's why we would call it the slow system, even though sometimes it's pretty And that is it. We're done with neuroanatomy, and I hope that hasn't been too much torture for you. There we go. I'll see you in chapter 4. Over and out.